Okay, so we have Inês Aniceto to talk about asymptotics of the late-time expansions in relativistic hydrodynamics.
Yes, thank you. And yeah, thank you for organizing this in-person meeting, which I haven't seen so many people together in such a long time, that it's really nice to actually be able to discuss just impromptu instead of having to, you know, book a meeting online and actually yeah, book ahead basically, which is definitely not the same thing. So yes, thank you for the opportunity to come and talk here as well. I'll be talking about so late-time expansions in relativistic hydrodynamics and how it actually very much relates to the subject of divergent asymptotics, and how actually one shouldn't be scared of getting results that don't seem to make sense, because sometimes the not making sense brings us to a lot more information than we thought in the first place. So why care about relativistic hydrodynamics? Well, so what we hope for with relativistic hydrodynamics is actually to effectively describe strongly coupled systems. But of course, we don't want, so imagine that you have the core fluid plasma, the initial conditions, they're highly non-hydrodynamic, of course. But then you can expect that after a certain amount of time, they reach some sort of, they expand, they reach some sort of thermal equilibrium, and you could hope to have a theory of hydrodynamics that would effectively describe it at that point. Of course, if you're talking about solving hydrodynamics, you talk about having phenomenological parameters, and those have to be given in some way, so that you have a gradient expansion, you stop at some point in derivative expansion, but you need to have phenomenological parameters. And this is where ADS-CFT in some way comes in, especially if you're talking about particular theories. So these phenomenological parameters can be defined basically by the microscopic theory, which you're trying to effectively describe by hydrodynamics. And if that microscopic theory, of course, is a quantum field theory, like super-Young-Mills, n equals 4 super-Young-Mills, you can use that, and then you have the phenomenological parameters, and you can also, instead of solving strongly coupled super-Young-Mills, you can use ADS-CFT and actually solve Einstein equations to obtain the results that you need for the relativistic hydrodynamics. Of course, other microscopic theories exist, and also toy models that allow you to actually experiment a bit of what to expect instead of solving the full quantum field theory, which can be quite difficult as well. So, okay, what am I trying to solve? I'm trying to solve the conservation equations of the energy momentum tensor. I'm assuming, in terms of my strongly coupled system or my plasma, I'm assuming a lot of symmetries here, because I'm interested in general in super-Young-Mills. I will talk about conformal theories, of course. So the whole system of the energy momentum tensor is very constrained. In fact, meaning you have all these different parts for the energy density, the pressure as given by the equation of state, the flow velocity, and then the dissipative effects that are all in the shear stress tensor. And this is where all the phenomenological parameters come in as well. So if I'm assuming several symmetries, conformal symmetry, so I'm talking about an expanding plasma, I'm looking just at the central region, so ignoring what happens, at the edges, just looking at the central region, and I'm talking about that I'm expecting that the plasma, when it got created, that it's relativistic, and of course it has a boost invariance through the longitudinal region. This is called Bjorken flow, and so actually assuming several of these things, I can simplify my system quite a lot. And in fact, you can redefine everything in such a way that you only have a single function to calculate, and you can choose that function to be the energy density. Everything else can be described by that one function. So assuming enough symmetries, basically you allow to have something that, and not just that, it also only depends on proper time. So I have a function of proper time, which I want to calculate. Relativistic hydrodynamics, of course, if I'm trying to talk about the plasma, I'm assuming that my theory will describe the system towards later times when I can assume some sort of close to thermal equilibrium. So, meaning instead of trying to find this function to all times, I would try to do an expansion at late times when I expect that behavior to appear. And so, as I've mentioned, so you have your system, very highly non-equilibrium at the beginning. Eventually, it will transition to some sort of hydrodynamic behavior. And what you find, meaning if you assume conformal theory in your microscopic conformal theory, what you have for your energy density is an expansion of this type, so powers of in proper time. And what are all these terms? So these terms are actually quite simple, that this one alone describes that the leading behavior of your system is actually described just by the perfect fluid. But of course, because I said that I had the shear stress transfer with my phenomenological parameters, those will actually give me the dissipative effects that will be encoded in all these epsilon k's. So all of them will depend on these phenomenological parameters. So basically what I have is a dissipative hydrodynamics, and this expansion gives me the transition from whatever non-equilibrium state I had into like something that is hydrodynamic. So in terms of the superconducting plasma, of course, dealing with the strongly coupled system, this is it's a non-trivial, it would be a non-trivial ordeal to actually calculate things from the superconducting point of view. But you have ADS CFT, and you can have a map between your quantities in the CFT and a solution in gravity. And basically what you have, so you have, in the microscopic theory, you have your states that correspond to some black hole solution. In particular, assuming a flat space at boundary, what you have on this side is black brains. Then this perturbative non-equilibrium phenomena, but when I'm talking about perturbative non-equilibrium phenomena, I'm talking about this transition to hydrodynamics. What you find is that you have linearized perturbations around the black brain solutions here. And then you find even more than that, in fact. So you could say, this is what I want up to here. That gives me my late time expansion. But in fact, you have more than that. You have non-hydrodynamic degrees of freedom. You can find them. And these actually correspond to exponentially decaying quasi-normal modes from the black hole perspective. So this is a map. You can, like I said, what you do is you calculate these perturbations on the gravity side, not on the superconducting side, and then you can just translate it, and you have your energy density for your strongly coupled plasma.
Can I ask a question about the previous slide? You have this expansion. So are terms, are funny things like logs of tau divided by powers of tau not?
So actually, when you're calculating things, especially from the gravity point of view, they show up, but they end up adding to zero. So you end up without them. I think this might not be a general case. That you might have theories. So superconducting mills definitely you don't have. You actually might have theories with that, but this wouldn't. Such things would not. From the point of view of what I'm talking about, would definitely not be a problem. Whether that would actually be a problem from the point of view of physics, on the other hand, I think. Meaning having log of tau as a proper description of hydrodynamics, I wouldn't be completely sure what that would mean, in fact. Because
Can I also ask a question? The initial conditions, do they have to be essentially, okay, the non-equilibrium, but do they still have to be conformal, so to say, in a way? Or can they be anything, and does the non-conformality decay more rapidly?
no, I would assume that the whole theory is conformal, yeah. To the point that I think that if you had something non-conformal as initial conditions, you probably wouldn't be able to actually do a lot of the work that the asymptotics actually allows you to do in this case. So just very quickly, that in this case for Superyoung-Mills, the dual geometry, you have your metric, your 5D metric, and you basically want to solve the Einstein equations. You expand them very close to the boundary, and you take the z to the fourth term, basically, and that is actually, so you can calculate the energy density by calculating the limit close to the boundary of the function A, meaning coming from this first perturbation. So, of course, I want the late time expansion, which means that I want A at late times, and you can do this by proposing ansatz for these functions that are an ansatz at late times as well. So you can obtain all these different things. Of course, meaning I will give results from both perspectives, but Superyoung-Mills is quite a complex system in the end, and what I want to give you is a general perspective of why these things work and what we can do with some of the tools that I'm going to talk here. And for that, I'm going to go to a toy example in some sense. So what I want is a model that allows me to generate the hydrodynamic gradient expansion. So my late time expansion coming from the fact that I'm expanding the shear stress center tensor up to some order. And that exists. There's the Mueller-Israel-Stewart approach that allows you to embed hydrodynamics, make sure that you have relativistic causality. So you basically introduce some relaxation time for the shear stress tensor, and by doing that, what happens is that those, I mentioned non-hydrodynamic degrees of freedom that were related to quasi-normal modes of the black brain. Here, you also introduce non-hydrodynamic degrees of freedom, exactly because of the relativistic causality, and this basically gives you kind of a toy model that mimics what happens with the Superyoung-Mills case. So again, I want to study the evolution equations. I'm assuming the symmetries that I have assumed before, so I've mentioned this. You approximate the shear stress tensor by corrections to the ideal fluid, and you obtain, there's different assumptions, but I would say that probably the simplest one leads you to a first order nonlinear ODE, and so this F is the pressure anisotropy. It's, again, we're talking, as I mentioned before, we have a single function that we're calculating. So if I'm talking here about pressure anisotropy, it's directly related to the energy density. It's a very simple relation. And Z is basically the proper time. It's proper time times temperature, but it's directly related. And of course, like I said, because I'm talking about the gradient expansion, I have phenomenological parameters related to the viscosity and the relaxation time, which got introduced by the shear stress tensor. And those basically are why we have viscous hydrodynamics. So this is much easier to solve than Einstein equations, obviously, and it's also a very good way of analyzing what we expect to see. So I did mention that, so I'm trying to analyze a fluid strongly coupled. I wait enough time, and I expect it to be described effectively by hydrodynamics. But, meaning I expect this at quite late times. As it happens, so of course the initial conditions I expect it to be extremely, meaning very, very different. The choice of initial conditions changes dramatically the behavior at initial time. But as it happens, sorry. As it happens, I mean, you actually have a transition to hydrodynamics, so you can expect, so this is meaning the behavior that you expect from our late time expansion, so that it is meaning that's well described by the late time expansion. But as it happens, you can go quite early, and even very, very early on, suddenly you have already that expansion being valid. So you don't have to go to very late times for our transition to hydrodynamics to be seen. And this was, meaning they've called this the hydrodynamization scales, which is that in fact the transition, the conversion to a hydrodynamic description happens while the system is still very anisotropic. It's still not close to thermal equilibrium, but somehow it works. And also, the hydrodynamic description really, really does not depend on the initial conditions. Somehow, the initial conditions, the information on the initial conditions gets lost halfway through.
Is that a consequence of strong coupling?
No, that's a consequence of it's.
So the transition time scale is set effectively just by the temperature inverse?
By the relaxation time, if I'm not mistaken. But it's mostly related to the non-hydrodynamic modes. And those are basically exponentially, they become exponentially close. So as soon as those non-hydrodynamic modes, which are the ones that govern the initial conditions, get exponentially close, you're left with just the hydrodynamic behavior. So because it can't be the strong coupling, because meaning everything here, even at thermal equilibrium, you're still talking about a strongly coupled system. So there's no, it's just that whether it's anisotropic or already quite isotropic.
Sorry about this one, but if you were to say in seconds, how long is that time?
And that's an amazing question, and I cannot remember, meaning I've seen it written in papers, approximations. It's a fairly small time, yeah. You're talking about, very, very close to the initial time. It's highly anisotropic and then suddenly collapses quite quickly. And then it stays, as a power law. Meaning there are, I think there's plots with actual time, proper time, in fact, instead of the weighted version as well. So meaning I can answer this to you once it's over. So how do we describe this very early convergence towards hydrodynamics? So basically, it's what I mentioned. So the hydrodynamic model contains these non-hydrodynamic degrees of freedom. They are non-perturbative in nature. They basically exponentially decay very fast. They play a major role at early times. They're very sensitive to initial conditions. But then at some scale, at the hydrodynamization scale, they're all exponentially close. So you don't see them. You can't distinguish between them, and you can only see basically what is left, which is the evolution towards the hydrodynamic state. This in fact this part is a hydrodynamic attractor. It's called a hydrodynamic attractor because it depends not on any initial state. It always goes towards that final state. But so one question that of course I would like to ask is, so okay, hydrodynamics works much earlier than expected. But is there even more there? Is there a possibility of going towards early times? They're definitely not hydrodynamic. is there more information than we'd hope somehow that beyond the hydrodynamics, even though we're trying to have an effective hydrodynamic description at late times. And in fact, there is. It's related to the fact that the series are asymptotic. So these series, the energy density is in fact, if you analyze these epsilons, these E's, for large enough K, so for an order large enough, what you find is that they diverge. So this series, you calculate the series, you're hoping to sum it, and you find that it diverges. So it grows factorially. Of course, you can't just sum it because you need to worry about the fact that you're going to get the divergent result. But the fact that the series is asymptotic is the reason why we expect this hydrodynamization scale, that we expect these non-hydrodynamic modes. And moreover, if we actually properly analyze it, we know that in these coefficients alone, you have all the information about this non-hydrodynamic modes and perhaps about the early times encoded. And this is called resurgence. So the early times resurge in the late time behavior of these epsilon Ks. So initial conditions are uniquely encoded in a set of parameters, and those set of parameters basically just determine the strength of the non-hydrodynamic modes. Oops. So, like I said, the series is divergent. It's resurgent in that sense that the early times, the early time behavior resurges in these epsilon Ks and the factorial growth of these epsilon Ks. But as I mentioned, so yes, we have hydrodynamics. It works at late times. It works earlier than the late times. But can it work at early times as well? Is it possible to work at early times? So can we match the late time behavior to any given initial condition? Can we describe the system at all times? And moreover, if we have somehow a good description like this, can we find analytic behavior just beyond the pure perturbation theory of the system? And this, to answer this, we go through stop a moment, talking about resurgence and asymptotics, where what I wanted to say is that because of this, so even though these series are divergent, what happens with asymptotic expansion is that they actually converge quite quickly. And what I mean by that is if you take just a few terms, just the very few first terms, you get really, really, really accurate results. So if you add too many, you get horrible results. But if you just add just right and just a few, you get really, really accurate results, much better than a typical Taylor series. Also, there's established summation methods that have exponential accuracy. So we were saying that initial times non-hydrodynamic modes will be exponentially close to each other. So we can't distinguish them. But if you had methods that sum my results that actually are exponentially accurate, then you're actually able to distinguish between these, and that means that you're able to distinguish between the initial conditions. And if you actually do that, you can indeed obtain global and analytic properties of the system, such as branch cuts, away from even the real line, which is the proper time. So this was a very, very long motivation. I'm going to stop a moment just to give a brief idea of the method and the summations that I'm going to use. It's going to be very general, not very precise in any way. But because I want to just give you the general picture of these asymptotics that allows me to then actually go back to my relativistic hydrodynamics models and actually see that indeed these models are resurgent, asymptotic, and that I can actually do this initial time, late time matching. So then I go very quickly through this. I start this. Definitely, meaning anyone who has done the double well, please, this is absolutely not correct. It's just an idea. Of course, because I'm not talking about instantons, anti-instantons. I'm just giving just a general picture. So you imagine the double well. you're trying to solve the Schrödinger equation. And of course, meaning you want to be the coupling very small. So you're very close to one of the wells. So how do you solve it? You can first take G equals 0, and then you have just the harmonic oscillator. You can solve it exactly, and you get your ground state energy. But then I can say, OK, let me just do a small perturbation, and instead of doing G equals 0, I do just G slightly non-zero. So just small, but greater than 0. And you can just try to use perturbation theory to solve it, in fact. And you do find a series. So you have a series in powers of the coupling G is H bar. As it happens, this series is asymptotic. It grows factorially. It doesn't just grow factorially. If you analyze it properly, you see that there's a subleading exponential growth. So it has a factorial growth, which screws up summing this in any proper way. But then you have a subleading exponential growth. And the fact that I wrote there A has an obvious meaning in this case. So we know from quantum mechanics, why is the series asymptotic? It's kind of the same way as with hydrodynamics. The series was asymptotic because we had non-hydrodynamic degrees of freedom. Here, the series is asymptotic because we have instantons, exponentially small contributions to my energy of the ground state. So basically, I have corrections to this, which are of this shape, of an exponentially small term. Of course, if I expand this exponential to small g, this is 0 to all orders, so I wouldn't be able to see it. But there's these corrections that come from instantons. So I did say it, so I have G very small. I calculated the ground state energy as a perturbation, so just a perturbative series. But I know I have instanton corrections, which I need to add. But I don't have just one exponential. I have multiple instantons, so I have all possible exponentials to add. So somehow, in order to actually get my full result, I need to add this all. And you could ask, why do I care? Meaning these are exponentially small. But the fact that you have an asymptotic series, that you have a divergent series, is the reason why you need to add these all, because these correct somehow the errors of summing the original series. And you have to add them all in order to get 0 error if you want. Another reason is, so you have small coupling. So at small coupling, I have all these exponentials that are small. But what if I wanted to go to large coupling? Then all these exponentials suddenly become of order 1. And that means that, you know, I better have them, otherwise there was no way I would be able to obtain the correct result at large coupling. So what you do is that you include all of them. So all of these are series. You include all your instantons, all your exponentials. Actually, there is a freedom, typically, that you have an extra parameter there. That parameter, that's what I said, encodes the strength of my instantons, the strength of the non-hydrodynamic modes. And basically, this is called a transseries. What is a transseries? Transseries just means that you're doing a series in not just your original parameter, G, but also in some non-perturbative terms, exponential of minus a over G. If you had logs, you would include logs as extra non-perturbative terms as well. And all of these series, in fact, are all asymptotic, are all factorially divergent, all of them. So I didn't mention, but this A, the reason why I wrote this A, it's a meaning why, because it's the instanton action. It's the probability of tunneling between the two minima of the potential. So each series is divergent. So now we go to the other thing. So what? So I have a divergent series. How do I know how to sum it? I told you that it's very accurate. You only need a few terms to get a very, very good result, exponentially accurate. But I need to know how to sum it. And in fact, that's why that I wrote here, that truncating it, if I truncate it just right, and there's a meaning to this just right, it actually provides a very accurate approximation. Oops. So in this, I'll mention what I mean by truncating just right. Imagine that you have a function, which is factorially divergent, and that you truncate it to n, and you define these fn's by a truncation up to n. If you compare your if you compare imagine that you can calculate this function experimentally, and you have my truncation up to n. What happens is that if I subtract them, if I compare them, the error decreases exponentially, so this is log, up to a minimum value. So there's an n optimal that I need to stop at, such that the error is as small as it possibly is, it can be. And then if I add any more, then it starts growing quite badly. So there's a value, and that value is actually given by the a over g of that exponential. Again, a is the instant on action, so we can calculate it. This is the optimal point of stopping. And you can see that the error between these two is exactly of that order, of the instant on. This is what I said, that if I ignore the instantons, I could never correct my result. But if I keep on adding, they keep on correcting each other, higher and higher.
I have a question, general question. So how do we know that the instantons are enough? So why, for example, why not to include also e to the minus a over g squared? So my question is influence of this conference, which is about string theory. We have both deep brains and S5 brains, and we can have contributions of the form e to the minus 1 over g string, e to the minus 1 over g string, and g string squared. So that's just, so the thing about, let's say, QCD is that we know that the instantons dominate the semi-classical functions. But once we enter the non-perturbative regime of strong coupling, we cannot be sure that we can saturate, and or it's a question actually, how do you know that you can saturate everything by instantons only?
So when I write this, basically the fact that it grows like that is related to having e of minus a over g directly. So there are, first there's generalizations of this that allow such exponentials to include, meaning in the theory of resurgence. I'm not talking about now of physics. So I'm not yet answering your question, basically. But so how would you know is you'd calculate these coefficients, you would analyze their behavior, their large order behavior, so for n large enough, and that would be where you'd find the information of what type of exponentials to expect. Because meaning I've written this, but actually, imagine that I assume that there were only these exponentials. I analyze, so if I assume this, the theory of resurgent of asymptotics tells me very, very explicitly how these coefficients grow, and not just the leading order, every single order in large n, for a large enough order.
So it's kind of an experimental observation.
So
that is sufficient.
So, meaning I would say that the first thing I would do is I would analyze and check that whether the ansatz that only this type of exponentials would show up is enough. And meaning you'd very clearly see if you were missing something.
So for example, I think what the kind of thing Adi is alluding to, maybe things like in strongly coupled Yang-Mills, you might have what you think is the instant-on action, but a fraction of that.
That would be extremely easy, but it's a very different thing to have exponential of minus something over g, and that something is very easy to find out, and then it could be renormalons, or it could be instantons, and it could be different objects. So fractional instantons. That would be very easy. That would be, you would directly see it from here. If you have now that something over g squared, that's a trickier thing, and you'd have to analyze it a bit further. I've never seen the examples of that.
I think, I would say, influenced by ADCFT, I would imagine that certain quantities in n equal 4 super Yang-Mills
Would have
should
that.
be in the partition function could, I think, should include such. So except, let's say, D5, let's say, graphing S2, I can imagine NS5 graphing S2 leading to such contribution. So I cannot see why in n equal 4 super Yang-Mills that's sufficient.
No. So this is the energy density of the strongly coupled plasma with lots of symmetry. So it's a very, very specific observable. And in this observable, it's, meaning we've done loads of tests. There's nothing else. Right. And also you can calculate it from...
It's an experimental observation. It's not a general answer.
It's not a so in some sense, the transseries, coming up with an answer for the transseries is an experimental observation. But you have very accurate tests that you can do, and if they go wrong, they go wrong because of these factorial growths. They go wrong really, really fast. And then you do educated guesses of how to change based on the physics and what you expect.
But is there any result of the type, if I know this number of coefficients, it's not indicated up to that order, then I know for sure I know everything?
So again, if you have, it depends on how many coefficients. If you have 4, I would say it's going to be very difficult to make a very, very obvious, to answer very, very decisively. But given how fast, because how fast these things go, even if you have 10 or 15, you already see that things are not working.
I think I'm more in the sense on whether there is a math theorem that says it may not be feasible to apply the math theorem. Is there a math theorem that says, you know, if you give the first, I don't know, n coefficients and there's this behavior, then you can make a respective function.
Oh. So it has happened in cases where this was true up to a point and then actually it just got truncated and I wasn't expecting. So I will answer that there's no obvious, absolutely general situation like that, but I would have to say that especially if you have, if you're solving some sort of equation, yeah, there are math theorems that you can kind of use to try and assure that, for example, the type of functions like the Gevrey-1 functions that lead to just these exponentials are the ones that you expect.
Like for instance, just think to this exotic brains that not like 1 over g squared. You have 1 over g to some strange power and so on. That people get by using the duality of the known objects. Should we worry about this number two with the effects? It's not just 1 over g squared, it would be 1 over g to, I don't know. Some strange
so the first thing that you would find is that the actual perturbation theory, the honest perturbation theory wouldn't be in orders of g to the n. They would probably be fractional orders in the perturbation theory as well.
By the way, we only know how to do genesis functions.
So it's g squared.
You may hope to get some feeling of the growth of these coefficients, and of course there are results.
So again, there is a part that is, there are actual tests that you can do, and there's the part about purely experimental. And the first thing you do is, like, you have your perturbation theory. You do, I'll mention this, meaning you analyze the singularity structure behind the factorial growth, and that singularity structure and the type of branch cuts that you get give you information about what to expect of the non-perturbative behavior. So you can analyze the branch cuts that you get. You can understand what's yeah, like I said, the type of branch cuts. If they're logarithmic branch cuts, you only have these exponentials. If they're more complicated branch cuts, then you're talking about a very different set of non-perturbative. So there are, like I said, there are definitely theorems that you can use to analyze, and you analyze by doing Borel transforms, basically. That's the first thing you do. So I've mentioned this. So this is just to say that what I already said. So you have your series. If I do truncate my perturbative series, I have an error that is exponentially small. That is exactly at the point where the one instanton series starts contributing. If I add them correctly and truncate this one in properly, what I get is then an optimal error that is now, so this is also has, the truncation of this has an error that is exponentially small. It's multiplied by another exponential, which means now that the error will be of double exponential. That's going to be now corrected by the second instant-on correction, and then on, and then on, and then on. So basically, what you have is adding more and more instant-ons, keeps on correcting and decreasing the error. But just to reiterate, the error is already exponentially small when we started from. So we're talking about a very accurate result already from the perturbative series alone. But just the perturbative series won't separate for me the different non-hydrodynamic modes. So I need at least include one exponential to actually have that distinction. And this is, like I said, this is all linked. They're all absolutely linked and very precisely linked by the theory of resurgence. So that's what I mentioned now. So how can I see evidence of resurgence if I have a series? And what type of exponentials do I expect? So I have a series. It's factorially divergent. I actually can calculate these coefficients numerically or analytically. And what I can do is actually do an inverse Laplace transform to each term. And if I do that, what I obtain, in effect, what I'm doing is removing the factorial growth. And I can analyze now this new series. So it's now a finite radius of convergence. I can analyze it. I can see the analytic properties of this new series. And so this is just a simplification. So I said that here it was approximately, right, behavior was n factorial. But let me say that it's exactly n factorial, just for the sake of simplicity. If you calculate the Borel transform, what you find is a pole at A. So basically, if I have just simple factorial growth with that subleading exponential growth, what I find in the Borel plane, so this is a Borel transform, it's a pole at A. Typically, we don't just have poles. That's meaning the fact that it's not exactly n factorial, but it's approximately n factorial gives you rise to a branch cut. What I want to say is that singularities in the Borel plane are related to the non-perturbative phenomena in my observable. There's not regular Borel transform, no. But there are, meaning there are generalizations. So, okay, can I associate, so I have my trans series, these are all expansions. Can I associate also a function to this, to these series? And I can sum, there are ways of summing these, like I mentioned, the optimal truncation. There's proper ways of summing all these, exponentially accurate. And what I do then, I have at the end that parameter sigma, which gives me the strength of the exponentials of the non-perturbative phenomena. And basically that is the one that is related to the initial conditions alone. So I've mentioned, so how to obtain a function? I need to sum. There are different ways of summing it. I'm going to mention 3 of them because they have all their strengths, different strengths. And they will give you, again, global analytic information. This is another thing, meaning you have here perturbative series, but actually you can go beyond that perturbative series and you can actually find analytic information about my observable. So these sums can be done for any value of G, typically. Of course, the larger the value, the more terms you would need, typically. And it can give you analytic data like poles, zeros, branch cuts. Can give you phase transitions if you're analyzing a partition function, for example, as well. You can do coupling interpolation or initial time to late time in hydrodynamics. So just very quickly, I mentioned the optimal truncation. So the optimal truncation is actually what is done for the perturbative series, and there's a point where you stop your series and you get an exponential small error. But of course, if I want to include the next instanton, so the one instanton in contribution, then what I'm doing is not called optimal truncation, just nomenclature, it's called hyperasymptotics. But there's still, there's completely well-defined formulas. These are formulas, it's not just obvious optimal truncation, but you do basically an optimal truncation with double the numbers that you had here. for the perturbative series, and then you include also the one instanton series, and you obtain an exponentially accurate up to the second exponential for your result, and you can still continue these things. The good thing is that there's no need of integrations or numerical integrations on these calculations, which is not the case with Borel resummation. So I mentioned the Borel transform, which removed that factorial growth and allowed me to analyze. But now, how do I go back to my function? I did an inverse Laplace transform before, so now I do a Laplace transform back in order to get my observable. So what I do is, like, for each one of the series, I can do the Laplace transform of whatever my function was. In that example that I gave, it was just a pole, so I just integrate this. So, but you can see that I can integrate it anywhere except in the direction that I have a pole. So these are typically the directions where I have singularities. These are called non-Borel summable, just because you can't integrate directly there. But you can integrate either above or below. And you can see that the difference between the integration above or below gives you exactly this exponential. So for the pole, it gives you not just approximately, but exactly that exponential. But of course, if I have a branch cut starting there, it will be an exponential times something else. So what I want to say is that integrating the information that I have around that singularity will give me something that is related to the next instanton. So basically, I have that. And in some way, if I did this Borel analysis, I could see what type of singularities I could have. And with that Borel analysis, so basically, if I have something that is expected to be something over g squared, it will definitely, the Borel plane will look very, very, very different. So that would be my first step into trying to understand what type of things we'll find. So, one last thing that I wanted to mention is transasymptotic summation. I'm going to go very quickly. It looks like a horrible formula, but the idea is that I'm here summing over all the exponentials, and here inside these, I'm summing over all powers of g. But I could change the order of summation and say, for each power of g, I want to sum all the exponentials. In fact, in many, many cases, you can do this exactly. So you have, for all powers of g, you can calculate this function. Tau is just this sigma times the exponential. And you can calculate these. And these now have a validity very different from what we had before. You can go much closer to the origin with this summation. And it allows you a much easier way of calculating, for example, zeros of a function that you didn't have before. So this is just one last summation. And now what I wanted is just very briefly to tell you how, in the examples that I actually started from, we talked about asymptotics. Now go back to the example of relativistic hydrodynamics. And the first I wanted to, is superior Mills plasma. So I said I could have a transseries. Let me tell you what the transseries is. It's a very horrible object. So you have an infinite number of exponentials, but all these exponentials are actually not just a, 2a, 3a, 4a. Because the quasi-normal modes, you have lots of different quasi-normal modes. For each one of the quasi-normal modes, you can have omega 2, omega 3, omega 4, omega, but you have an infinite number of them. So what happens is that you actually have an infinite number of possibilities of these exponentials. Of course, in actual calculations, you're interested in the ones that are least suppressed, typically. So you truncate this quite quickly. But still, this is so you have an infinite number of quasi-normal modes. You have an infinite number of parameters that would typically encode the initial conditions. And so, yeah, you would have to sum this. But again, you could go and actually truncate your series to the least, to the largest quasi-normal, to the smallest quasi-normal modes. So in terms of analysis, I said, I can grab the perturbative series. Let me see if there is resurgence. So it's factorial divergent. If you analyze the Borel plane, so I calculate the Borel transform, and I can see, what I see is, for example, not points, not singularity, not poles, but branch cuts. And the branch cuts are starting, so these are the first quasi-normal modes. You have omega 1 in blue, and then you actually have here and here is the 2 omega 1 and 3 omega 1. But then you have here another one starting at omega 2, which is a different quasi-normal mode. Here it's now starting at omega 3, which is yet another quasi-normal mode, and you also have the complex conjugate here. So you can directly see where the singularities are. Of course, you can calculate the quasi-normal modes from different ways, which means that you actually know exactly where these start, and you can analyze the type of branch cuts that you have.
What are the axes?
So this is the Borel plane. So when you go to...
The orange plane.
It's just that, so if you saw all possible exponentials with all possible n's, you could state that these points are also allowed in those exponentials. But actually, from resurgence, if you did the analysis of resurgence, you know that they can't be there because they're multiplied by 0. And in fact, for so they would be there, for example, for the one, if you analyze the first quasi-normal mode, the perturbative series in the first quasi-normal mode. But they won't be there for the perturbative series. And one of the things that we wanted to show, and this is from the paper, wanted to show is that indeed, meaning even though, they show up as exponentials, the resurgent formulas say they're not there, and indeed, they don't show up.
Are these actually branch cuts? Or
branch cuts. So how do we actually analyze this? We approximate the Borel transform by a Padé approximant. The Padé approximant has only poles. So in fact, what you're seeing is an accumulation of poles. But in the actual function, if we could go beyond an approximation, or if you use different approximation methods that allowed branch cuts, you would see branch cuts there. They're log branch cuts.
Sequel to that, how many orders of resolution here are we talking about?
Here for this one, I think is about 300, something like that. Meaning we calculated lots of different quasi-normal modes to 200 orders. So once the machinery is working amazingly enough, it actually, meaning you can do this without, meaning in a couple of days, not in a couple of months, in fact, but yes. And we calculated these, of course, all from the gravity side. So again, so now about the MIS hydrodynamics, it's now a single parameter transseries, so much simpler. So I have just one type of exponential and all possible, so exponential minus a, minus 2a, minus 3a, etc., all with series. These are factorially divergent. So the a and the, well, here there's the beta as well. Doesn't quite matter, but they're related to the relaxation time, for example, the A. And so the relaxation time gives you the scale at which this actually goes to the hydrodynamic behavior. But more than that, what I wanted to say is about the early times, and I'll finish with that. The early times to late times. So you have a finite, so here I know that from the solutions that there's at initial time, there's a finite solution here. And also, there's a whole string of infinite solutions that behave like this at initial times. And what I want to know is if I can compare, this parameter sigma with, in particular, this parameter c, which is the parameter that gives me the different solutions at the initial times. In fact, you can, and this is what you get. You get you do an interpolation, and you obtain exactly sigma of c here. That's for different values of c, you get the imaginary part. There's extra things. There's an ambiguity in calculating this. The imaginary part is fixed. You can find it that it's fixed and it's correct. It doesn't matter. But the real part, definitely, there's an obvious matching, and you can do this matching. But the main thing is, like, you're starting at late times. You have the non-hydrodynamic modes, but you can still go to the match with the initial time condition solutions. And so this is just a moment about that if you did transasymptotics, in fact, you can sum these functions, you obtain them exactly, and moreover, you can find the branch cuts of the solutions, and you can approximate them asymptotically. Because they're asymptotically, the further away, they're more accurate. But basically, these values are, in green, is you can predict them exactly. So you can use these sums to predict more things than just a matching, even from early to late times. And just to say so, this is this is just a plot of the comparison, numerical comparison, and the various summations. But so I talked about the hydrodynamic gradient expansion, saw that it succeeds at very early times, but even more than that, you can go all the way to initial times, that the asymptotic properties encode everything. So yeah, in the Coles multiple scales of early and late times, and you have very known, accurate summations that you can use. Of course, you can go much further. There's other microscopic theories. If you have multiple non-hydro modes like superring Mills, you could still hope to fix the first parameter sigma such that you'd still obtain an approximation of the early times. And you can even, meaning then you can analyze, like I mentioned, zeros of partition functions for phase transitions. You can analyze bifurcation phenomena with these methods, of course. And yeah, distinct regimes of asymptotics. Imagine that you have asymptotics at IR, asymptotics at UV, and you wanted to kind of match by doing some sums of this type. And thank you. Yes. So, meaning it depends on what you mean by you know the not. So if you knew because when you calculate the quasi-normal modes, you also have a series associated to it. So if you don't know the series, you only have the value of the exponential. So you have information there, of course. You have. So yes, did you see the transasymptotics? If you had the first term, meaning maybe, I guess that, no, actually, because it's the parameters. So imagine that you're doing transasymptotics, which means that you're actually summing over all the exponentials. So you'd have the first term of that series, which gives you some information about some regimes. But that also depends on whether you have some sort of initial conditions known or not, because the parameter sigma come multiplied by the first exponentials. But so the short answer is perhaps. It depends on what you know. You don't need the series. You could do this type of summation, like I said, of summing all the exponentials instead of summing all the series for each exponential. And you could try and analyze the system in a different regime. But just from that, you couldn't, for example, get, apart from getting the first term of the original series, you couldn't get beyond that.
I think these quasi-normal modes at large frequencies, they sort of become evenly spaced, and it's sort of asymptotic formally for the quasi-normal modes, so that like some WKB type.
Yeah.
Does that
So.
mean anything? So could I get, for example, the asymptotics of this surface series? Could I find asymptotics of the quasi-normal modes? They tend to be quite simple, like the large omega, the large frequency.
So the problem is that with these, meaning it sees much more strongly the leading order quasi-normal modes as opposed to the very far away ones. So without any other knowledge, you would have to actually, in the end, unfortunately, you would have to know the previous orders in order to get to the very late one. No, I would have said that very likely, unless you went to, you had a very special situation, you'd always see the leading ones, the smaller ones first, no matter what.
So we have a break now, but before, and some people are rushing off. I suggest we all